Good morning, sir.
So is it visible? So only 35 people have joined, okay? Is it visible?
Yes, sir.
So if you recall what we have studied in the last class, we have started the consolidation. Uh, so consolidation, so what is the consolidation? Generally, it is the expulsion of water from the soil due to long-term loading. Okay, expulsion of water. We have initial consolidation, intermediate, primary, and the final. So primary consolidation is very important. So spring analog we have seen. Then we have seen the how the consolidation we generally determine in the laboratory also. Okay. So why we have to study this consolidation? Because with load, what happens to the soil and how much it will compress, okay, consolidate, how much it will settle. This is of our interest because when you construct a building, so because of the heavy load, so we will simulate it for this load, this much is settlement, for that much, how much can be the settlement, so that we can, there are some laws, okay, whatever results we are getting in the laboratory can be simulated to the field also, okay. So likewise, uh, it is very important property, okay, consolidation. It is an engineering property, I would say. It is not index property, okay. There is a difference between index and the engineering property. So permeability also engineering property, shear strength also engineering property, consolidation also engineering property. So these properties are used for our construction, okay, in the field, to find the settlement. There are permissible settlement also. For a clay soil, maybe generally 40 to 50 is permissible settlement, okay. So more than, if the soil settles down, then you can observe cracks in the building and building may sink, okay, collapse. So likewise, IS code has given some permissible settlement also for different soil, different foundations and so on, that you will see, okay, in next semester. But in the today's semester, today's class, so we just focus on this consolidation. So in the laboratory, we have seen there would be some cell in that we'll keep this soil sample and we'll try to apply different load and we'll find out the final wide ratio and so on. Okay, and we can drive plot load versus, I mean, wide ratio is keep on changing. Okay, keep on reducing. So with the load intensity, okay, but how generally we find this wide ratio? Load anyway we know, stress anyway we know, load divided by the area. But how generally we find wide ratio? Because we cannot measure directly, right? Wide ratio is volume of white, volume of solids. Either we should have other property, specific gravity and other degree of saturation and so on, okay. Then only we can, water content at least. So then only we can measure this wide ratio. There's no direct method to measure the wide ratio, okay. So now in today's class, there are two methods. Okay, this is what we have seen last class. We use porous stones and other thing, both on top and bottom, and likewise we can find out. So here in this consolidation chapter, we generally plot the E versus log P curve. Okay, that anyway we'll see. So how generally we determine this wide ratio at various load increment? How do you know what is the wide ratio there? Then only how do you know? Without knowing, how we can plot this wide ratio versus stress or increasing stress? So this, there are two methods for finding this wide ratio. First one is the height of solids method, and second one is change in wide ratio method, okay. So let us see first height of solids method. Okay, in this method, equivalent height of solid is determined from the dry mass of a soil. Okay, the height of solids can be given. Hs can be written as volume of solids divided by cross section area of the specimen. So how we can write this volume of solids from the definition of specific gravity? What is the definition of the specific gravity? Density of solids to the density of water. Density of solids can be written as mass of solids by volume of solids. So likewise, we can write this particular volume of solids is equal to mass of solids by specific gravity multiplied by density of water. So this particular term will come from the definition of the specific gravity. If you are not following also, you just check the definition of the specific gravity, which is density of solids to density of water. Okay, density of solids can be written as mass of solid to volume of solids, and volume of solids can be written as mass of solid divided by g gamma w. Okay, rho w multiplied by 1 by a. Here Hs is the height of the solids, Vs is the volume of the solids, Ms is the dry mass of the sample, G is the specific gravity, A is the cross-section area. Okay. Now what is the definition of E here? Volume of voids to the volume of solids. How we can write this volume of voids? We can write as the total volume minus volume of solids will give the volume of voids divided by volume of solids. So here this equation again can be written as area into height minus area into Hs, volume of solid, height of solids, okay, divided by area into H of solids, okay. R can be written as H minus Hs divided by Hs. So here void ratio can be measured with respect to H minus H is the height of the solid. So here I mean total thickness after your consultation the experiment gets over, we can find out the total height, total thickness or the initial time. Okay, so thus the wide ratio is determined from the total height and the height of the solids. The total thickness of the sample is measured at least once during the test, usually either before the start of the test or at the end of the test. Okay, at other stages, the loading, the thickness of H is worked out from the measured thickness. Okay, and the difference in the dial gauge reading. Okay, so once we measure it initial thickness, then what we'll do is this change in thickness can be measured with by the using the dial gauge reading. H we can get it as H naught is initial height. Okay, initial height we know. Okay, plus or minus change in height. So H can be find out as initial height plus or why plus or minus. Generally you may say that sometimes the soil height is because of load, sometimes height is always reduced. It's not the case always it will reduce. Okay, what happens if you measure the dial gauge reading, the soil may also swell. Okay, so because of the water and all, it is in fully saturation condition, so soil also little swell also. Okay, so that's why we are writing as the H naught plus or minus change in the height. No, it is given by this one beautiful example, or they have given exact in the tabular column. Now let us look at this table column. Okay, here applied load is 0, 10, 20, okay, kilonewton per meter square. We are increasing the load here. Okay, then we are observing the dial gauge reading. False dial gauge reading is 490, 482. Okay, the least count of the dial gauge reading is 0.01 mm. Okay, so how we can find out the change in the thickness now? Okay, here nothing, the change is same. Okay, starting initial, after that change in thickness 490 minus 482. How much? 8 you will get. 490 minus 482. Okay. 8 is reducing from 490 to the 480 to reducing. 8 multiplied by 0.01. The least count it will give 0.08, like 0.12, 0.36 here. What is happening is after that 249 the reading increases. Okay. I mean unloading will do it. Okay. When you remove it, the soil will try to swell it. okay, with the zero load. So we will unload it. When you unload it, okay, then what happens? The dial gauge reading comes here. So that's the reason it is plus. Now how we can find out this change in height now? Initial height we know here. Suppose this is the computation of the void ratio by height of solids method. Here what are the parameters are given here? H naught is given, initial height 25 mm is given, area of the specimen is given, volume is given, mass of solids is given. That means we know that how to find mass of solids, okay, dry solids, not the soil, mass of solids, specific gravity and the water content is given, okay. So how we can find out this one? H naught we know 25, okay, plus or minus this one 24.92, minus this one 24.80, and so on, so on, so on. And then from H minus HS, how we find the HS generally? HS we can get it from this equation. Mass of solids we know, specific gravity we know, density of water we know, area we know. We can find out this HS by using this one. Okay, so H minus HS, we do calculation like this. What is the definition of void ratio? H minus HS divided by HS will give the void ratio. That means initial void ratio was this one, 0.754, then keep on decreasing, 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 0.748, 0.740, 0.713, 0.684, and so on. So what we have done here exactly, at a different stages of a load, we are able to find out the void ratio by using the height of solids method. Understand? So likewise it is given here, some calculations are given how to find HS. HS is the H minus this one, whatever you have used that formula, HS, once you get it, void ratio you will get it, okay. Here E naught is the initial void ratio, at the start H naught we have to take. After that intermediate stage void ratios, these are the intermediate stage void ratios, okay. Then once you know this all void ratios and this load applied, we can draw these graphs easily, is it not? So these graphs we can draw easily. So that's how they, so then one more method is change in void ratio method here. So how generally you find out the void ratio? Again, change in void ratio method. In this method, the final void ratio E final, okay, corresponding to complete swelling conditions after the load has been removed, is determined from the water content. We know this formula, AC by G equal water content. AC, here AC is the 1 because fully saturation. We know this formula, okay. E is equal to AC equal to WG, okay. So here AC is equal to 1 because in the saturation, in the consolidation, soil is in a full saturation state, okay. So the final void ratio corresponds to the complete swelling. First what we'll do is final void ratio we'll find out, okay, using this formula. Then for stage wise we'll find out the void ratio corresponding to intermediate stage is determined as explained below here, okay. Here what is the definition of void ratio now? Void ratio is equal to volume of void to volume of solid. Volume of void can be written as total volume and volume of solids divided by volume of solids. So here we can write is as Vs cancels. We can write this one, take this one this side, okay. Then V can be written this in this way, okay. So how we can write this V into H we know, area we know, suppose we can be written in this way, okay. Then what you do is do the partial differentiation, okay. ADH equal to VSD, and when you do partial differential equation from this C and the B equation, you will get this equation. These are known factor for us, okay. We know the void ratio of a soil, we can find out the void ratio of a soil, okay. And we know the change in height, we know the initial height, we can find out the change in the void ratio at a different stages, okay. Understand? So likewise we can get the change in the void ratio at a different stages. Once you go get the change in void ratio, okay, this final void ratio we know, change in height we know, we can find out the change in the void ratio. Okay, this is one more method they have given it, okay. Here the same equation here, whatever here it is showing, the same equation, this and this equations are same, okay, both equations, okay. Now let us take our here also one example. Okay, so here how we can compute the void ratio by changing void ratio method. Initial height is given, area is given, volume is given, mass of solid is given. Now how we can find out the G is given. Okay, final height is given. I mean, okay, so how we can find out here? Again, apply load here. Then take a dial gauge reading like we have done it. Change in height we can find out easily by using dial gauge reading. H is given. Okay, height is initial height we know, H naught we know. Okay, and change in height we can by using change in height we can find out this 25 minus this one change in height, this you will get it. But change in wide ratio, how will get it? Change in wide ratio by using our formula, whatever formula we have derived it. Okay, here 1 plus, how we get this wide ratio? Here by using our water content and G, it will give wide ratio, final wide ratio. Okay, so 1 plus 0.066 divided by H is gives will give the multiplied by change in height will give the change in the wide ratio. Once you know change in wide ratio and the initial wide ratio or final wide ratio, if you know it, just deduct it from bottom to here, go up. Okay, it will give the wide ratio, all wide ratio at a different stages. Hope you are following. If you are not following also, no problem. It's very simple. Okay, one reading is enough. Okay, so what we are doing here is we are by using our consolidation test, we will conduct consolidation test for a different increment of load. For different increment of load, what I am doing here is I am finding the wide ratios. Okay, from the height anyway we can find out by using the dial gauge readings. Okay, and once you find out this wide ratio versus load increment curve, now actual real picture comes into the play. So these are the things what we do is consolidation results, how general will present it. So why we are doing it anyway, there are some basic definition here to find out. Okay, when you try to plot a graph, okay, here for a clay soil, slowly with the time the dial gauge reading reduces and it will attain a small constant value. But when you conduct on a sandy soil, generally we compare it to sandy soil. Suppose we generally don't do for consolidation, what happens? Dissipation of the water takes place very quickly. Okay, because permeability of sand is very high. Here the dispersion of water, the expulsion of water takes very slowly and the graph you will get like this. But in this case sandy soil, if you compare a graph, you will get like this. So that's what is they have drawn the graphs for a sandy soil, and here on the right hand side we can plot these effective stresses versus the void ratios. And generally what we do is, because the graph is coming in a curve form, we generally plot in a log curve actually. Okay, so instead of plotting like this way, okay, uh, we when you plot this particular stretches, okay, E log, we call it as E log P graph, very famous. Okay, E log P graph that we'll do in our the consolidation. So likewise, like if you recall in shear strength chapter, by using triaxial test we used to find the Mohr circle, if you recall. Okay, more circle sigma 1 sigma 2 sigma 2 anyway we are neglected, sigma 1 sigma 3 sigma 1 sigma 3 sigma 1 sigma 3. Okay, in the normal axis, y axis will be shear. Okay, shear, x axis normal. Then we have plotted number of more circle, then we have joined with the tangent, then where it intercept, what we found was the C, and the angle whatever it get, it give the angle of internal friction. That means the soil which have internal friction, angle internal friction, the soil, which soil will have more internal angle of friction? Sandy soil will have more. Clay soil doesn't have any angle of internal friction. What it is having? Cohesion, that is only C. That means the particular whatever the tangent you draw would be horizontal for the clay soil, horizontal for the clay soil. There is no internal angle of internal friction, only intercept, that is cohesion. The soil, the clay soil will have cohesion. Okay, internal angle friction phi will be almost negligible, or we can say zero. Will always take zero for a clay soil. Okay, so likewise, remember in this particular uh, chapter, always by using this, we generally try to plot the E log P curve for a consolidation, that you remember. So everything is based on this E log P curve only. Okay, so slope of this E log P curve is called the coefficient of compression index. Okay, so there are some basic definitions are given. Okay, and this particular, if you see this particular curve, generally what generally we do is in consolidation, we not only do loading, we do unloading also. Understand? To know that how much soil will swell actually, how much it will rebound, or we can say come to its original position. So soil is not an elastic material, so that it won't come back to original position. Okay, but it will attain some rebound. Okay, so that's the reason what generally we do in the laboratory test after applying seating load, like we have seen yesterday, we will keep on applying stresses. Okay, uniform stresses, and then after final that one, dial gauge reading, again the same pattern will remove the load, unload. But when you do the unloading, the curve may not follow the same path, it will follow the different, that is what it is given, unloading. Okay, unloading path. Again, if you reload, it won't follow the same path whatever we loaded initially, right? So here there are a lot of changes is taking place in the soil. Void ratios are changing. Okay, so that's what it is given. Okay, unloading and the reloading. Okay, this is what the figure has given. So after sample has reached the equilibrium, effective stress sigma 2. Okay, as shown by the sample B, the pressure is reduced and the sample is allowed to take up the water and the swell. The curve BEC is obtained in unloading. This is known as the expansion curve or a swelling curve. Okay, it may be noted that the soil cannot attain the void ratio existing before the start of the test, and there is always some permanent set or residual deformation, because soil is not a plastic material, it is plastic. Okay, soil is a plastic, not a elastic material. Okay, so if the soil specimen which has swelled to a point C is reloaded, the recompression curve CFD is obtained as the load approaches the maximum value of the load previously applied corresponding to the point B. Okay, there is a reversal of the curvature of the curve, and then the plot DG continues as an extension of the first loading uh, curve. However, the reload specimen remains slightly lower wide ratio at the point D than that of at the point. So this is what generally we do it. Okay. So generally we plot in E log P curve only. So here we log curve we use it. Okay. This test anyway we will do it when you return back to the NIT. So we have this consolidation test. So okay, I'll ask you to prepare a sample and apply load, and if I'll ask you to draw a curve. We can easily draw by using the dial gauge readings. Okay, so that's what it is involved. So so all these states are, see, maybe in the next class we can see some basic definition. Okay, so all these tests may be included in the appendix. Let me check it in this book whether we have it or not. So somewhere at the end, uh, whatever test we generally use for your laboratory, I think it is there. So when you go through this one, okay, it will give laboratory experiment. It will give far I don't know, I mean understanding of this subject. Okay, so there are experiment like to determine the water content of a soil by oven dry method that we have seen. Okay, just keep the sample in the oven dry and find out the water content. So how it is done? Okay, in the laboratory it is given very clearly method. Okay, and then what is the second one? Determine water content soil by picnometer. Okay, this one. Okay, then third, determine specific gravity of solid by density bottle method, that also we have seen how we can find out the specific gravity of a soil. Determine the specific gravity of solids by one more method. Okay, picnometer, that also we have seen. Then we have seen some video to determine dry density of a soil by core cutter method we have seen. Okay, This formula, we know that once you know this water content and density, this is the bulk density, we can find out the dry density easily, and determine the in situ density by sand replacement method we have seen to measure the volume. Okay, so this is the procedure is given, sand replacement method. Determine the density of sample, water displacement also can be done. Then particle size distribution sieve analysis we have seen, okay, by plotting the graphs, okay, mass retained and percentage retained and calculation of cumulative retained and so on. Percentage finer y-axis and x-axis can be done, and we can plot these graphs and we can find out, okay. So likewise, hydrometer analysis also we have seen, liquid limit we have seen, plastic limit we have seen, shrinkage limit we have seen. So these are the tests is included in your laboratory. When do you have this laboratory actually? Next semester or this semester? Is somebody taking this laboratory? Nobody is taking the laboratory course now?